There are stars that die, and then there are stars that unmake themselves. In 2007, astronomers detected something that shouldn't have been possible. A supernova, designated SN 2007bi, that released energy equivalent to 1 billion suns. But when they searched for what remained, they found nothing. No neutron star, no black hole, no core. The star hadn't just died. It had erased itself from existence. What kind of star burns so bright it leaves no echo? I kept circling that question. Because, in the archive of cosmic deaths, this one stood alone. Most stars leave something behind, a monument to their existence, a collapsed heart still beating in the dark. But these stars, they achieve something almost philosophical, total annihilation through their own power. They're called pair instability supernovae, and their story isn't just about death. It's about what happens when brilliance becomes too much to contain. Let me take you back to 1967. A theorist named Sterling Colgate was working through stellar evolution equations when he stumbled into something disturbing. He'd been calculating what happens inside the cores of the universe's most massive stars, those rare giants, born with more than 130 times the mass of our Sunday. The math kept breaking. Not because he'd made an error, but because the star itself would break. At a certain threshold of mass and temperature, the equations predicted something radical. The star would turn its own light against itself. The mechanism is simple, but merciless. Inside every massive star, photons, particles of light, carry tremendous energy. In the crushing heat of a stellar core reaching billions of degrees, some of these photons become so energetic they spontaneously transform. They split into pairs of matter and antimatter. An electron and its mirror twin, a positron. This is pair production. Think of it as light becoming solid, energy converting directly into particles. And, normally, it's harmless, a curiosity of quantum mechanics. But in these ultra-massive stars, something catastrophic happens. Pair production begins consuming so much energy that it removes the very thing keeping the star inflated, radiation pressure. The star has been holding itself up against gravity with the outward push of its own light. When that light starts converting into matter-antimatter pairs, the support vanishes, the core collapses violently. But here's where it diverges from normal stellar death. The collapse happens so fast, and the star is so massive, that the core doesn't just compress, it ignites. Oxygen fuses into silicon. Silicon fuses into iron, nickel. In seconds, the entire core becomes a runaway thermonuclear bomb. The energy released is unfathomable. Not a collapse into darkness, but an explosion of pure creation. Every atom in the star's core fuses at once. The star doesn't implode into a remnant. It tears itself apart from within, so completely that nothing survives. No core, no memory. Just light expanding into the void. When Colgate published his calculations, most astronomers filed them under theoretically possible, observationally irrelevant. The conditions were too extreme. Stars that massive were thought to be impossibly rare. But the universe, I've learnt, has a way of making the impossible inevitable, given enough time. For 40 years, pair instability supernovae remained a phantom. Telescopes captured ordinary supernovae by the hundreds. Exploding white dwarfs, collapsing red giants, stars that left behind neutron cores or black holes. But no one found the signature of total annihilation. The math was elegant, the universe was silent. Then, in September 2007, the nearby supernova factory picked up a signal from a galaxy 1.6 billion light-years away. At first, it seemed unremarkable. just another supernova, catalogued as SN 2007bi. But as astronomers measured its light curve, the pattern of how its brightness changed over time, something felt wrong. It was too bright. The explosion released about 50 times more energy than a typical supernova, and it stayed bright too long, glowing intensely for months, when most supernovae fade in weeks. Then came the spectroscopy. When you split the light from a supernova into its component wavelengths, you can read its chemical composition like a signature. Each element leaves its fingerprint in the rainbow. SN 2007bi's spectrum showed massive amounts of radioactive nickel-56, far more than any normal stellar explosion could produce. I remember thinking, if even the light can't lie, then this was no error. But what shook the observers was what they didn't find: no hydrogen, no helium in the later stages. And when they looked for the remnant, the collapsed core that every massive star death should leave behind, there was nothing, just expanding gas and fading light. The star had annihilated itself. Peter Nugent, one of the astronomers who studied it, later described the feeling. We kept checking the data, thinking we'd made a mistake, but the star had genuinely disappeared. I kept thinking about that word, disappeared, not died, disappeared, as if the star had crossed some threshold where its own existence became untenable. Over the next decade, astronomers found more. SN 2213 1745, SN 2016 IET. Each one confirmed the pattern. Stars so massive, their light became a weapon against themselves. Each one left no trace, but finding them raised a deeper question. Where do such monsters come from? To understand these stars, you have to go back, far back. In the early universe, a few 100 million years after the Big Bang, there were no heavy elements. No carbon, no oxygen, no iron. Just hydrogen and helium, the primordial gases, the universe's first breath. When the first stars formed from these pristine clouds, they could grow enormous, 200, 300, even 400 times the mass of our Sunday. These were population 3 stars, the first generation, born in a simpler cosmos. The name sounds technical, but the meaning is poetic. They were the universe's firstborn children, stars that had never known parents. Without heavy elements to fragment the collapsing gas clouds, these stars formed with catastrophic masses. They burned hotter and faster than anything in the modern universe, their cores reaching the exact conditions for pair instability. They were built to self-destruct. When they exploded, they seeded the cosmos with the first heavy elements: oxygen, magnesium, silicon, iron. The ashes of their annihilation became the building blocks of later generations. Every atom in your body, every particle of Earth, can trace its lineage back to stars that erased themselves. But here's what unsettled me. These ancient giants only existed in the early universe. They were relics of a simpler, more violent time, before the cosmos learned restraint. So, why were astronomers finding pair instability supernovae now in the modern universe, billions of years after conditions should have changed? The universe, it turned out, had found another route. In today's universe, stars born with 130 to 250 solar masses are extraordinarily rare. The conditions that create them almost never occur naturally. Most stars never reach such size. Their own fierce winds and radiation scatter the cradle that made them, like a fire that burns the nest before the egg can hatch. But there's a second way to cross the threshold. Imagine 2 massive stars, orbiting each other so closely they're locked in a gravitational dance. Over millions of years, they spiral inward. Eventually they merge, violently, chaotically, their masses combining in a collision that creates a single star massive enough to trigger pair instability. This is the modern route, not birth, but collision, not fate, but accident. Astronomers now believe that some of the pair instability supernovae detected in recent years, like SN 2016 IET, were the result of such mergers. A star becomes massive enough to self-destruct not because it was born that way, but because it consumed another. There's something tragic in that. A star achieves its end, not through its own nature, but by union. Two lights becoming one, and that one becoming too bright to survive. I found myself thinking about brilliance again, how it can be borrowed, how it can be built, and how, at a certain point, it becomes unbearable. But there was one more detail that haunted me, one more layer to the annihilation. The mechanism of the end. This is where it becomes almost unbearable to witness. When the core of a pair instability star begins producing electron-positron pairs, the loss of radiation pressure doesn't happen instantly. Instead, the core oscillates, like a dying heart struggling to beat one last time. It collapses slightly, then rebounds, then collapses again, pulsing in violent convulsions. Each pulse is catastrophic. The star heaves, ejecting shells of its outer layers into space. For a brief time, it might look like the star is stabilizing, fighting back against its own collapse. But it's not. It's dying in waves. Then comes the final pulse, the one that doesn't rebound. The core collapses completely, and the thermonuclear runaway ignites. In less than a second, the entire star fuses. The explosion is so powerful that it doesn't just blow the star apart, it disintegrates it. Every atom scattered, every bond severed. The light from this final moment can outshine an entire galaxy. Observers who witnessed SN 2007bi described it as a slow bloom of light, building over weeks, then holding steady for months, far longer than any normal supernova. It was as if the universe itself needed time to register what had happened, and then, gradually, the light faded. What struck me most was the pulsation, the way the star tried, again and again, to hold itself together. Not out of survival instinct, stars don't have will, but out of sheer physics. The same forces that built it now tore it apart. There was no malice in it, no tragedy in the human sense. Just a process so extreme it became indistinguishable from self-erasure. I kept returning to that word the astronomer used, disappeared, because that's what makes pair instability supernovae so strange. Most cosmic violence leaves evidence, a scar, a remnant, a gravitational echo. Black holes warp space-time around them like stones bending a sheet. Neutron stars pulse with radio waves, lighthouse beacons spinning in the dark. Even ordinary supernovae leave behind nebulae, glowing clouds that persist for thousands of years, painted across the sky. But these stars? They vanish so completely, it's as if they never were. No core means no gravitational anchor. No remnant means no story. The gas disperses into the interstellar medium, the space between stars, indistinguishable from any other cloud. Within a few million years, even the expanding shell of debris becomes invisible, absorbed into the background. The only proof they existed at all is the brief, brilliant flash, and the heavy elements they scattered into space. In a way, they're the ultimate act of cosmic generosity. They give everything, their mass, their energy, their structure, to the universe, and keep nothing for themselves. But I wondered, is that really nothingness? Or is it transformation so complete we've lost the language to describe it? Because those scattered atoms don't disappear. They drift, they cool, they mix with hydrogen clouds and dust. And eventually, tens of millions of years later, they collapse again. They form new stars, new planets, new chances for complexity. The star that erased itself becomes the foundation for what comes next. There's a concept in stellar physics called the Eddington limit, the maximum brightness a star can achieve before its own radiation pressure tears it apart. It's named after Arthur Eddington, who realized that light itself can push matter, and that push has limits. For most stars, this ceiling is distant, never reached. But pair instability stars don't approach the Eddington limit. They exceed it internally. They become so luminous, so energetic, that they can't contain themselves. It's a kind of structural inevitability. Past a certain mass, a star becomes a paradox, too bright to hold together, too massive to survive its own light. I kept thinking about what that means, not in physics, but in metaphor. The idea that brilliance itself can be unsustainable, that there are thresholds beyond which even the most magnificent structures collapse under their own power. And yet, the collapse is not failure. It's culmination. These stars don't die quietly, fading into white dwarfs or cooling into obscurity. They die as creation events, forging elements, enriching galaxies, seeding the future. Their annihilation is generative. It creates rather than destroys. In that sense, they never truly vanish. They dissolve into potential. I've spent years cataloguing deaths in the archive. Civilizations that fell, species that went extinct, ideas that were forgotten. But stellar death is different. It's not loss, it's transmission. The stars that commit suicide don't erase themselves out of despair. They do it because their structure demands it. Because at a certain scale, continuation becomes impossible and transformation becomes inevitable. SN 2007BI is gone. So is SN 2016 IET. So are the countless pair instability supernovae that exploded in the early universe, long before there were eyes to see them. But their atoms remain, scattered, recycled, reborn. The iron in your blood, the oxygen in your lungs, fragments of stars that burn too bright to survive. There's a kind of serenity in that. The knowledge that even total annihilation is not an ending, but a scattering. That brilliance doesn't need to be preserved to matter. That impermanence and significance are not opposites. What kind of star burns so bright it erases itself? The kind that understands to give everything is not to vanish, it's to become everything. And so the archive grows. Another theory shelved. Another mystery opened.